All right, we've got 25 minutes to talk about Neville's method. I guess that's impossible, but let's try anyway. Let's start talking about Neville's method right away in tabular form. And so I'm going to have a spreadsheet open and also have paper. And the function we're going to interpolate here is a nice function. F of x equals e to the x. And we're going to interpolate over the interval from 1 to 2 effectively. You can see in the spreadsheet that my nodes are labeled over here. 1, 1.2, 1.3, 1.5, 1.8, and 2. I've got 6 nodes there. X0 is 1. X1 is 1.2. X2 is 1.3. X3 is 1.5. X4 is 1.8. X5 is 2. And I purposely made them unequally spaced because the method, just like with Lagrange interpolating polynomials, still works even when they're unequally spaced. What does Neville's method do? Big picture. Neville's method is essentially, in the background at least, about using Lagrange polynomials of higher and higher degree to approximate functions like e to the x. Yes, for any value in some interval, like the interval from 1 to 2, but when you actually make the table in a spreadsheet or by hand, you're thinking about one value of x. Like in the spreadsheet here, it's 1.42. So I'm trying to approximate e to the 1.42. What is it more precisely? The spreadsheet, to get the spreadsheet to do it, I need exp v1. That represents e to the 1.42 power. Spreadsheet doesn't have a built-in number e. You have to use this function exp. Represents e to the x. 4.137-12044. We can confirm it with a calculator. E to the 1.42 power. 4.137-12044. Yes. Okay, so there's what it is. Accurate to 8 places after the decimal. How can we try to approximate that with Lagrange polynomial based on some nodes, in this case 6 nodes, which means we need a degree 5 polynomial. I guess I should say degree at most 5 polynomial, without actually doing what we did in section 3.1 and actually coming up with the formula for the polynomial. And if we're going to do that by hand, that would be nasty here, right? Degree 5. There'd be a lot of calculations to do by hand. I mean, you could try using Mathematica, and that's probably better, but is there some recursive way to do it that's set up relatively nicely for spreadsheets to do, and maybe only uses numerical values instead of function formulas? That might be nice. Again, function formulas, polynomial formulas are in the background. What do? It's going to be handy for us to figure out x minus xi for each I. In the lecture I made 3 years ago, I actually did not do that in the spreadsheet I made that time, but this time I'm doing it. So a spreadsheet formula here, the value of x is in cell B1. I'd want to do $B $1 to make that an absolute cell reference. The first dollar in front of the B keeps the column fixed. The second dollar in front of the 1 keeps the row fixed. It actually would be fine just to keep the row fixed, but, and that's handy sometimes to not keep the column fixed. But for most applications, to play it safe, put $2 signs. Minus xi is in B5. Don't use dollar signs there because you want it to change to B6, then B7, then B8, then B9, then B10. So 1.42 minus 1 is 0.42. 1.42 minus 1.2 is 0.22, etc., including some negative values. This first column after that point, you can see is labeled P sub I, and also Q sub I comma 0. This is consistent with the labeling in the book. Having one subscript under the I, or under the P, I should say, emphasizes that the values in this column are going to come from degree 0 approximations. Having one subscript for the P. Having two subscripts for the P in this next column emphasizes it'll be degree 1 approximations. Having three subscripts for the P in the next column emphasizes it'll be degree 2 quadratic approximations. So as we go across the columns, the degree of the underlying polynomial is getting higher. In the end here, I'm after degree 3, 4, 5. I'm after a 5th degree approximation in the end. I could add more columns to get higher degrees as well, but based on, I'd have to have more nodes if I did that though, right? Based on 6 nodes, labeling 0 through 5, I'm after a degree 5 approximation in the end. The Q's represent the same numbers, but the subscripts are always 2 of them, and the second one is first 0, then 1, then 2, then 3, etc. So you could think of the second number as representing the degree, or the column number starting with column 0, 0th column, 1st column, 2nd column, 3rd column, which matches the degree of the underlying polynomial. And the I matches, you can see the last number, the last subscript of each P. Effectively, that represents the rows. It represents these I's here. 0th row, 1st row, 2nd, 3rd, 4th, 5th row. Always starting by labeling at 0. So if these are degree 0 approximations, I guess those are just function values at these nodes. They're constant functions. They're constant polynomials in the background. Horizontal lines as graphs. Just take exp of these numbers, of the nodes. First one's going to be e to the first power, e, 2.71828. Sounds like it's repeating, but of course it's not. You know, in the background, e is an irrational number. Doesn't give us more decimal places, though I guess I could probably do something to give more decimal places. No, this is my, okay, yeah. There we go, a 3, it's not repeating. The next number is going to be e to the 1.2. 3.320116992, etc. So these are the function values. The last one's e squared, 7.389. In the background, linear polynomials, graphs that are horizontal lines. For sake of time, I'm not going to draw them because we don't have a ton of time here today. I maybe should make some drawings here, but not at the moment. Next column, remember, is going to be degree 1. No, not just one of them, a bunch of them. We're going to use, in the background, a bunch of degree 1 Lagrange interpolating polynomials based on these nodes. How can you do that if there's a bunch of nodes? How can you find a linear function? Well, if you were doing it statistically, you could try to just find the trend, but we're not doing it statistically. We want linear functions that go exactly through points. In other words, so for example, the first linear function should go through the data values for the first 2 points, the first 2 nodes, the 0th node and the first node. The second one should go through the data values for x1 and x2. The third for x2 and x3. The fourth for x3 and x4. The fifth for x4 and x5. First, second, third, fourth, fifth. I'm going to need 5 numbers here, but wait a minute, I've got 6 rows. Where do I put them? Well, by convention, the one that interpolates between the values at the 0th and 1st nodes, x0 and x1, will go in the row labeled with I equal 1. And then 2, then 3, then 4, then 5. Just a convention. How do you do it? So this, the one that goes in this first spot here in cell E6. I is 1, is evidently labeled P. Well, okay, the Q labeling is Q11. That corresponds to the P labeling being P01. Looking right here when I write that down. And thinking about the fact that in row 6, I is 1. And it's a recursive formula that takes the values, 2 values in the previous column, and interpolates between them effectively. These are functions of x. I probably should put the x's in there. Though, in reality, for the spreadsheet, I'm thinking about x as being the specific number 1.42. The formula in the book looks like this. You take x minus the 0th node times the number that you could label P1 minus, and here's where the book has some typos. They put a plus sign there. It should be a minus. X minus x1 times the value in the table labeled P0. All over x1 minus x0. So for this example, let's write this out by hand for this example. And then we'll get the spreadsheet to confirm the answer. P0 is this number, 2.718288183. It's E in this example. P1 is this number, 3.320111692. So what are we going to get here? When x is 1.42, we'll get 1.42 minus x0 is 1. That's a 1 there. Minus 1. P1 is the 3.320111692 minus, running low on room here, 1.42 minus x1, which is 1.2. I can't keep writing to the right here. I'll go off my paper. You can keep writing to the right on your paper. Times P0, which is E, 2.718281828, blah, out of room again. All divided by, that's a times there. By the way, that's a dot. All divided by x1 minus x0, 1.2 minus 1. The values of the differences here, here, and here. Well, no, these two differences, excuse me, are in the table. They're in this column. That's the 0.42, and this is the 0.22. This one down here is not technically in the table. It is the difference between these two numbers. It's 0.2. All right, let's see what happens when we compute this with a calculator. The numerator is going to be 0.42 times 3.320111692. I'll just enter that first. And then minus 0.22 times 2.71828818283, say. It's the number E. Looks like the numerator is 0.796427. Divide that by 0.2. And looks like we get 3.9821355521. Does that make sense? What are we doing? We are effectively finding the straight line between the nodes x0 and x1 and their function values to the right. We're effectively extrapolating here. We're taking a straight line, and because 1.42 is bigger than both 1 and 1.2, we're going to the right further than 1.2. We're taking that line and using it to approximate the function. So we should get a bigger number than 3.32. And we did. And because 1.42 is further to the right of 1.2 is compared to 1.2 and 1, we should expect to get a number slightly more than the difference, adding the difference of these two numbers to this one. The difference of these two numbers, 3.32, 0.11, and 2.7182818283. That difference is 0.6. If we add that to 3.32, 0.11692, it will still not quite be as big as the approximation we got, but it should be close. 3.92 compared to 3.98. It's because, again, 1.42 is 0.22 units to the right of 1.2, whereas 1.2 is just 0.2 units to the right of 1. We are using a straight line determined by these nodes, the first two nodes, and their function values to approximate the function at 1.42. We're assuming e to the x is straight line, but it's not. But it's a linear approximation. The interval is not too big, so maybe it's not that bad, is the idea. So how can we get the spreadsheet to do this? This is tricky. Watch. Maybe rewatch this video or watch the other lecture. Take the x value minus, just like I did by paper. I'm effectively trying to program this here. X minus x0, I already have it in column C right here, C5. I don't need parentheses. C5 times P1, which is right here, not in the same row. So we're going diagonal. Then minus x minus x1, which is in cell C6, right there, times P0, which is in cell D5, like an x. All divided by x1 minus x0. Use parentheses. This formula is copy and pastable. And is that a good idea? Yeah, because this one is going to interpolate the data points corresponding to nodes x1 and x2 and these two values. This one's going to interpolate the ones corresponding to x2 and x3 and their values. This one between x3 and x4 and their values. This one between x4 and x5 and their values. So these are linear approximations to e to the x, different linear approximations that are then being used to approximate e to the x when x is 1.42. Different approximations based on different pairs of nodes. The next column is quadratic. And for quadratic, we need 3 nodes. So the first quadratic, whose value we're going to put right here in row 7, we're going to use the first 3 nodes and their outputs. The second one, we'll use these 3. The third one, we'll use these 3. And the fourth quadratic, we'll use these 3. And the formula is not the exact same as this notationally, but it's a similar pattern. I'm not going to take the time to write it down. Listen very carefully. what do? X is still the same. It's still in cell B1. This first, here's the trickiest part. This first one is going to do, once again, X minus X0. This number right there. Times, we want to use the preceding column now, column E instead of column D. This number right here, diagonal. For you, from your perspective, it's a diagonal like that, okay? Minus X minus X2 now, go 2 spots down. But then times P0, 1 there. So the X has become a little off kilter in what's getting multiplied here. But that's what you want to do. And you watch the lecture, you'll see me do that. Divided by X2. Oops, what happened? Do that again. Okay. This times this minus this times this, all divided by, in parentheses, this minus this. And here's the most magical part about all this. This is a quadratic polynomial that's going to approximate e to the x using the first 3 nodes, 1, 1.2, and 1.3, and the outputs of those first 3 nodes. But notice I never used the first node, seemingly. Well, I did. It's in E6 and E7. The information at the X1, 1.2 is in these cells implicitly. But as far as using these 2 cells, you don't have to use them. That's the quote unquote magic. Those numbers are all pretty close together. And they're all not too far away from e to the 1.42. These are 4 different quadratic approximations. Now we're on to the cubic. 3rd degree, we need 4 nodes in each case, and there's going to be 3 cubics. First one using these 4, next one using these 4, and the next one using these 4. And it's a similar kind of pattern, but tricky. Once again, we use in the first entry of this column, which will be down in the row that you see here, we use this very first x minus x0 times this number that is in the same row minus this one, x minus x3, times this one that is just 1 row above, divided by x3 minus x0. And again, so even though we're not using the information over here, it's implicit in these numbers. And this gives us even better approximations. These are cubics. Compare with this. Then we go on to quartics. Same pattern. This times this minus this times this divided by this minus this. Can you remember that? Well, you can rewatch our class today or the lecture. Finally, we're on to degree 5. This will be our quote unquote best approximation. Actually, it's not guaranteed to be the best approximation, but you would expect maybe it is, or likely is. This times this minus this times this, all divided by this minus this, which is 1. 1.13712, 1617, 1.13712. Okay, we're finally off in the last three decimal places. What's the absolute error here? Absolute error, or just error. I'll just call it the error, which could be positive or negative. It's the actual value, which is in cell B1, right? Minus this approximation. Whoops. Not cell B1, B2. B2. On the order of 10 to the negative 6 with the negative sign. Actual minus approximate is negative. The approximation is slightly too big. Okay, so that is a real quick intro to Neville's method. In that other lecture I made 3 years ago, I go through lots of details with the actual polynomials themselves and graphs. It's worth watching if you've not watched it yet. And try to do the reading. I'll highlight the typos.